Good afternoon. My name is Michał Ślaski, and I'll be presenting lessons from Erlang. A short timeline and my background before we start. Erlang is quite an old technology. How many of you had a chance to try the Erlang programming language already? Yesterday, yes, indeed. We had a 2-hour-long workshop on Erlang yesterday with quite a few people attending, so I recognize faces. Erlang started in Ericsson Software Lab in 1987. This is quite some time ago. I was 6 years old at the time. And then, initially, it was internal technology for Ericsson. In the 90s, they've been building ATM switches with Erlang and some other telecom-grade software and hardware. In 1998, it has been released as open source. It happened that actually at the time I was about to start studying at the AGH University in Krakow. And then in 2005, the Erlang virtual machine gained support for SMP. So it could take advantage of the multi-core or multi-CPU architectures. And this is when I joined Erlang Solutions. I just graduated, and I work at Erlang Solutions ever since. So today, what I would like to focus on is maintenance of software. We are all developers. We love to talk about how to develop systems, how to design them. But frankly, development is just a fraction of the whole lifetime of a system, especially the one which is running on the server side. Those are the kind of systems that I focus on, and those are the kind of systems that my discussion today is dedicated to. So maintenance takes quite a chunk of this life. It could be even 20 years, where development only takes several years. So it's good you have good tools and programming languages and libraries and frameworks and whatnot to ease and speed up development. But it's equally, if not more important, to be able to maintain the system so that you can go on holiday, you can have your Christmas party, you can relax, sleep at night. So I will now go through some of the Erlang properties, some lessons learned from the 20 over years of Erlang development that I think are crucial if you want to have peace of mind when system went live. So it's not only about Erlang. If you find any of those ideas inspiring, maybe you already have tools and practices in the technology you currently use. Maybe there is something that needs to be done to improve the situation. So it's not necessarily that you need to use Erlang. But I think it's important to learn from it what really helps in production systems. One is OTP behaviors. This is actually just another name for design patterns. And while common design patterns like client-server, finite state machines, those are commonly used, Erlang has also application and release design patterns. So what is it for? It helps have consistent maintenance procedures. For example, we can produce one tarball artifact, which is a self-contained system which can be deployed into production system. So really, the deployment of a system is very important that it is a streamlined process, reasonably easy to repeat in any environment. Some people will develop on Windows, some other on Macs, when typically you would deploy server-side systems on Linux, Unix boxes. It's good to be able to deploy systems easily across those platforms. For those of you who have attended the yesterday Erlang workshop, this is the very last slide we had. For those of you who haven't, I have this Erlang workshop project on my GitHub, if you would like to follow. And at the end of this workshop, we got to the point where we were building this tarball, which is a self-contained system. You can see that it consists of the bin directory, the runtime system, all necessary Erlang libraries, and some configuration files which go to the releases directory. And you unpack, untar, and you're good to go. Being Abacus would let you start your system. Easy, easy deployment, very important. Another one, robustness. There is no way you can develop a system which is bug-free. No matter how hard you try, how many good testing procedures you have, there will be always some unexpected conditions on the production system. Be it the users that misuse your system, be it some network glitches which make your distributed system hard to debug or well, behave. Something which will be unexpected and never reproduced in a test environment. So instead of trying to defend and ensure that we never go into a failure situation, Erlang has adopted let it crash philosophy. Let it crash says, if you cannot deal with the problem, it's something unexpected, don't bother. Let it go, let it crash. There will be some other system, some other process observing this activity, and if something bad happens, it should know what to do, how to resume or restart. So let it crash is good, as we believe in the Erlang community, as it helps building resilient to bugs systems. We have a concept of so-called supervision trees, where some processes in the system, this represents an Erlang process, are supervisors, and they keep an eye on their children, on their workers. So this is a supervisor and a worker. If something bad happens in a worker context, the supervisor will get notified. So this actually helps you keep your code concise, because you don't need to assert that all the input data that you got into your function is really correct. You just assume that it is correct, so you proceed as it would be just fine. And if it happens runtime that you discover that certain input was wrong, or you were not prepared to handle some input, don't bother, crash. We can have many workers, many supervisors, so this is a tree, truly tree, which spans. And this is how a typical Erlang system will look like. So be prepared for a failure. Don't try to mitigate it too much. Distribution. On the server side, almost every system is currently somewhat distributed. It could be this is a cluster. It could be that it has to communicate with other systems over network. Systems are distributed. Erlang runtime system from the very beginning has distribution built into the VM, into the language. So it's network-aware runtime system. What is it for? Apart from building distributed systems, like the React database, which takes advantage of this, for anybody else, it allows also to do some interesting stuff with Erlang systems. For example, remote Erlang shell. Say you have already a system running on several Erlang nodes, and you need to connect to them just to check health, to debug something. You can remote connect to it with an Erlang shell, which is like read, eval, print loop, and execute any operation you need, and then disconnect from this node. Oh, actually, a number of tools have been developed around this Erlang distributed protocol that observe some target node and give you some instant feedback about the health and whatnot. I'll give you some examples. Before there, just wanted to quickly sketch what really Erlang distributed is like. So in this slide, the box represents an Erlang system. It's an instance of the Erlang runtime system, Erlang VM. Typically running on some dedicated box, but not necessarily. You could have more Erlang VM instances running on the same machine. Now, there are two boxes, each one running some Erlang. Erlang node typically has a name, and nodes can be connected. So the arrow represents a connection between two systems over network, a TCP connection, and we have two Erlang nodes. If you would execute a BIF nodes on one of those, you would see cat and flee as the list of two nodes. And assuming we have two such islands, so we have two small clusters, where nodes on the other one would execute and return dog and bird, we can connect them. As soon as any node on the left-hand side connects with any on the right-hand side, they start to auto-discover each other. And we get a fully connected mesh of network connections. Those are TCP direct connections between any given pair of Erlang nodes. So whenever you want to communicate from one node to another, it's always a one-hop operation. So enough of this, but what is it useful for? I believe everybody is familiar with Unix or Linux tools like Ntop, where you can see a list of all system processes running in your operating system and some statistics about each one of them. So a similar tool has been developed for Erlang. There are quite a few of those, actually. The one I picked here is called Ntop. And it looks very much like the usual Ntop. You also have a list of Erlang processes. Those run inside the Erlang VM. They do not use the OS level threads. Erlang VM implements its own scheduler and own system of processes. But it's very convenient. I mean, I bet everyone had a chance to try Ntop the other day and saw how useful this can be. So here we take advantage of Erlang distributed to connect to any arbitrary Erlang node that we happen to have in our network, and we can get this instant feedback. Very useful. Something goes wrong, you start to see some CPU cycles being consumed, unusual behavior of the system. You can quickly connect to it with the Ntop, see what's going on. Who is consuming memory? Who is using lots of reductions? Very useful when maintaining a large system and troubleshooting them. Another one, hotcode loading. Erlang VM has some properties which allow you to swap Erlang modules on the fly. Even if you are running hundreds of thousands of processes in a system, still you can load new version of a module into memory and swap those modules, and you have full control over when each process in the system can actually start executing code from the new module. What for? First of all, actually, it can help shortening development cycle, by which I mean, imagine you have some large system that you're developing in small increments, so that you do small change, you want to recompile and check it, and then you small change, recompile and check it. In a large system, which, for example, needs quite some time to boot, because it connects, initialize some states, whatever, there is no need to restart the whole system. You just upload this module or reload the module, and you already can test it and get quicker feedback on whether your change really helped or not. But forget about development cycle. This actually allows non-stop operations of a system, so that you can update the system on the fly with no downtime. It's not easy, because then you actually have to have very strict process of version control, and you need to be careful, but still the possibility is there. There are already some presentations out there on Erlang conferences where people describe very large-scale systems with no downtime. supporting millions of users connecting, for example, to chat, in-game chat system. No downtime for those systems. And then tracing, which I find the most interesting feature of the Erlang VM, frankly speaking, as far as the production system is concerned. Because this tracing is built into the VM. Maybe some of you had a chance to use tools like dtrace or systemtab or any of those tools which allow you for kernel space or user space tracing. But those tools require your kernel, your system, to support such tracing. I don't think such tools exist for Windows platforms, for example. I mean, dtrace-like tools. Or at least I have not heard about such. This tracing is built into the VM, and it allows you to turn it on and off per process, so it doesn't have to be a heavy operation. Even if you are running a system with hundreds of thousands of users connected, still you can cherry pick one particular user and start tracing his behavior. And you can trace function calls, any function calls, message passing, garbage collector behavior, some other system events like schedulers and such. But if we just take the function call tracing, how many times did you experience a situation where it would be so good if you had this printout in your code just right here, but you didn't? The so-called dupa debugging, where you put all of those small printouts here and there just to understand what's the flow of the system. I bet you've run into such a situation once or twice. So imagine that this can allow you to have live debugging session and no need to instrument code and then recompile. Because you can enable this dynamically in a running system. And then provide some pattern. So what is it exactly that you want to trace? Already some good tools have been built on top of this feature. I'll just quickly explain how this works, just to ensure that everybody is with me on the fact that it's not an overkill feature. The way it has been implemented is that every time the Erlang VM calls a function, Erlang is an interpreted language, so it is interpreted by the VM. Every time we call a function, we have this one extra operation, which if no tracing, it will just proceed and execute your standard instructions. If we do turn tracing, it actually will jump to this trace pattern that you provided, execute it, and then continue with execution. So as long as tracing is not on, it's cheap. As soon as it is on, it can become expensive if your process is executing very many operations and you happen to tracing every single function call. Of course, this can actually result in a flood of messages. So you need to be careful with this on a production system. But in a truly concurrent system, typically you do not have intensive operations per process. It's more that you have many processes executing in parallel, which makes up for the load. In other words, tracing a process in the system is not that expensive, even if the system as a whole is under some pressure and load. So getting back to some tools built on top of the tracer. Redbug is one of them. It's built on the Erlang trace function. And it allows us to define patterns. So we say what function we want to trace, what function call we want to trace. We could have even some more sophisticated pattern here, which would provide also some conditions. For example, we only want to trace function calls when the first argument is greater than this, or so some additional guard functions could be provided. For simplicity, in this example, I'm just providing a very simple pattern which says every time a process calls module lists function seek, which is a sequence of integers from x to y, then, well, let me know. And also, I would like to see what was the return value returned from this function. So then in my second line, I am in Erlang shell, I type list seek15, which produces a list of 5 elements. I mean, I'm now in my Erlang shell, so I do get this constant feedback. I know that it was me who executed it. But typically, if you're tracing some processes in the system, which, for example, handle TCP connections and some traffic from users, you don't know what's going on. And what happened here is the Redback has printed 2 events. One, about the fact that a process with PID32 called list sequence with these parameters. You can see which process called which function with what parameters. So you have all you need. This is what you would typically put in your printout. And then once the function returns, we also get an event, and we can see what it returned. A list of 5 integers. So now, with this output, I can refer to my source code and start to reason about it, where I have clearly seen what was the input, what was the output. I'm in a much better situation now to understand the behavior. If it is not enough, then I can keep diving into the source code, selecting some more patterns I would be interested in tracing, and keep expanding this so that I get more information until I nail down the behavior, bug, whatever. Maybe some of you have heard of flame graphs. It's a useful technique for profiling. What it does, it on some interval basis takes snapshots of stacks, and then it sorts them and can print them in a nice graph, which tells us in which functions typically a process spends time. And this is a very useful technique. It has been developed by one of the persons behind the dtrace implementation. So it's already used on the server-side systems. A similar tool has been built for Erlang. It's called eFlame. However, because it has been built through tracing, not through just snapshotting stack traces, we can also draw blocking calls, which in this graph are highlighted in blue. So not only we get this typical for flame graphs feedback about which function the process spent most time in, but also we see which calls were actually blocking the process, which is also very useful when trying to profile and understand what takes time. It could be that something takes time, but you hardly see any CPU used. So where does the process spend its time? Very useful. So again, flame graphs, actually it's a general technique. It can be used also for other systems, not only Erlang. Okay, so what's next? If this talk inspired anybody to try Erlang, then I would suggest watch Erlang the movie. It's a video that the 3 fathers and the godfather of Erlang have produced in the 90s to promote Erlang within Ericsson. Excellent video. #1 marketing prize. And then if you liked it, you may want to see Erlang the movie sequel. For those of you who attended yesterday, Gareth Smith was presenting. He's author of the sequel, which is targeted more to the modern audience. Then you may want to explore some open source projects. Just to name a few, RabbitMQ is a project in Erlang, Mongoose.im, React Database, CouchDB. Maybe some of you used some of those projects, didn't even know that Erlang has been used in those. Then there's Erlang community. We have erlangcentral.org, where you can find lots of tutorials, cookbooks, calendars and such. There are some Erlang conferences like Erlang Factory, soon in Berlin, in San Francisco next year. There's also Lambda Days in Krakow. This is a shameless promotion of Lambda Days. So if you're interested, submit your talk. And this takes us to my last slide, which is questions.
What do you think about the Elixir?
I think it's excellent for the Erlang community, which still has to learn a lot from, for example, Ruby community in terms of well, look and feel, the enthusiasm, the way the community operates. And the hope is that Elixir will bring this also to the Erlang VM. Not necessarily to the Erlang community, but to the Erlang VM and the tooling around it. So everybody's supporting this project as much as we can. Any other questions?
Hi, so in the beginning of the talk you mentioned how each node talks to every other node. If there are like thousands of nodes, won't that lead to network congestion or other scalability problems?
Probably it would. We don't build clusters of thousands of nodes. The biggest Erlang cluster that has been practically run in production was the RIA cluster with up to 100 nodes. So there are some attempts to improve this. There is an EU-sponsored project, a scalable distributed Erlang, which tries to actually, and not Erlang the movie, I can hear, is in the play, which instead of trying to connect every single node with every other node, will try to build some trees of connections. And this is proving to scale better if you need to build really large-scale clusters. A typical Erlang cluster would be tens of nodes, not hundreds of nodes. Any other question?
Okay, I'm here if you want to your right. Okay. Hi. So if tracing is so easy, what if you don't want anybody tracing your code? Can you protect against it?
No.
Okay.
Once you have access to an Erlang VM, then it's sort of public. I mean, you do not have Erlang source code, but you can trace anything. But even without this, as long as your system supports system trap or dtrace, you would have the same visibility into what your program really does. Okay. So it's like equally good or bad.
Yes, here. So I saw once a talk from a guy his startup was building microservice architecture based on Erlang VM. So basically his idea was I have servers with just one Erlang, and when he was building different services in different languages, he was wrapping them in to make believe Erlang, which each process was kind of Erlang process. Truth is, inside of it, it was different language service implemented in different languages. And we were just talking via Erlang messages. So my question is, it sounds like a very interesting idea, My question is, but his things was very custom built to his own startup. My question is do you know of any projects like trying to solve this kind of idea, and if it sounds like a good idea to you, and if any open source project which is trying to build this kind of system?
So if I understood the question right, you're asking what are the possibilities for interoperability between Erlang and other technologies?
I mean, I saw the example of doing it in a custom way by one guy, but my question is there any, of any projects who are trying to solve this in a more general way?
Mm-hmm. There is a number of ways to interfere with Erlang system from some other technologies. One of them is indeed implementing Erlang distributed protocol. We call those C nodes because there are already C libraries for building such C nodes. And this could be C, C++ system which behaves like it would be an Erlang node and can communicate over Erlang distributed protocol. So this is one technique, and it is sometimes used indeed. Maybe the startup you mentioned actually exercised this idea. There are some other techniques. For example, there is a protocol BERT invented by one of the GitHub founders, as Erlang has been used at GitHub at some point, which simply takes the Erlang term to binary function, which serializes any Erlang term and implements encoders, decoders in other languages, so that we can easily send Erlang terms to other systems, and those terms are somehow casted to data types specific to given technology. So this is then no longer a C node, it's more like RPC over BERT protocol. Those are the two that come to mind. I know that also Thrift has been used and some other things have been used. Those two I would say are most pure.
Okay.
Any other questions?
This may be a bit similar to the other question, but Erlang is maybe not particularly designed for sort of number crunching or processing heavy stuff. It's more like, optimized for the networking message passing style. So I'm wondering, like, are there many use cases of people using Erlang for the kind of network part of the stack and then selling out to some asynchronous, maybe stream processing in a more sort of crunchy language? And what kind of programming model are people using there? I'm just wondering how that kind of architecture plays out.
I think it deserves some larger discussion, so I'll just try to answer this quickly, and I will be happy to continue any other discussion after my talk. There are some attempts to prove that actually, for example, image processing could be done with Erlang. There was an interesting talk by concurrent a year ago, I think, about running image processing on a multi-core system with Erlang, which was outperforming many other technologies. So something that you wouldn't really think of as a natural use case for Erlang, proven to be pretty good. But it's true that it's not like you will build graphical interfaces with Erlang or mobile applications, or there are a lot of other use cases which are not suitable for this language. This was meant to be used in ever-running systems which are typical for servers, not necessarily front-end. I think it's enough. So I will be very happy to continue and answer some other questions after the talk. Thank you very much.